Today, we're going to pull back the curtain on the devices you use every single day. Your phone, your laptop, even your watch. We're going to uncover the hidden genius that makes them all tick. And it really all comes down to one thing, a secret blueprint. Think about it. You get a new phone and it feels absolutely amazing, just blazingly fast. But then, a year later, it starts to feel a little sluggish. So you upgrade and the whole cycle starts over again. What is actually changing under the hood that gives you that incredible feeling of speed? Well, it's not just one thing. It's a whole symphony of really, really clever design decisions. And that's exactly where computer architecture comes into play. You should think of it as the master blueprint for a processor. It decides not just what parts are inside, but exactly how they all talk to each other in the most efficient way possible. And, understanding this blueprint is really the key to understanding all of modern technology. So let's start right at the heart of the machine, the central processing unit, or the CPU. It's not just one big block, it's actually made up of a few key components, and each one has a very specific and absolutely crucial job to do. Okay, first up, we've got the control unit. This is kind of like the project manager or the traffic cop of the whole CPU. Now, it doesn't do any of the math itself. Instead, its job is to grab instructions from memory and then direct all the other parts, telling them what to do, when to do it, and where to send the results. It basically orchestrates the whole show. The real number crunching? That happens right here, in the arithmetic logic unit, or ALU. This is the calculator of the brain, right? Every single time your computer adds two numbers or compares if one thing is bigger than another to make a decision, the ALU is doing all that heavy lifting. It is the absolute core engine of computation. Now, for the ALU and the control unit to work at these insane speeds, they absolutely cannot afford to sit around waiting for data. And that is the whole job of registers. Think of them as the processor's own tiny personal scratch pad. These are unbelievably fast little storage spots that hold the exact piece of data being worked on in that very nanosecond. And that brings us to one of the biggest, most persistent challenges in all of computer architecture. How do you get data to the processor fast enough? It's a massive problem, and it requires a really clever, multi-layered solution. So here's the fundamental problem. A processor can do calculations way, way faster than it can pull data from the main memory, which is RAM. To put that in perspective, it's kind of like your brain can think up an entire novel in a second, but your hand can only write one word per minute. That huge speed gap creates a bottleneck, and it's famously known as the memory wall. Without a fix, our super-fast processors would spend most of their time just, waiting around. The solution is this elegant idea called the memory hierarchy. It's a tiered system. So at the very top, you've got those tiny lightning-fast registers. Just below that, you have slightly larger but still very fast storage called caches. Then you get to the bigger, slower main memory, or RAM. And way down at the bottom, you have the huge but slowest storage, like your solid-state drive. The whole goal is to keep the data you're going to need most often as close to the processor as possible. This really highlights the extreme trade-offs that architects are always dealing with. On one side, you have registers. They are physically inside the CPU, they're unbelievably fast, but they can only hold a few bytes of data. On the complete other end of the spectrum, you have RAM. It's a separate chip, it's much slower, but it holds gigabytes of information. The entire system is just this constant, delicate balancing act between speed, size, and of course, cost. Okay, so we've got the components and a smart way to manage memory. But of course, the architects didn't stop there. To squeeze every last drop of performance out, they invented these brilliant new processes for how the work actually gets done inside the chip. The big insight here was realizing that you don't have to finish one entire task before you start the next one. It's just like building a car on a modern assembly line. You break the process down into different stages, and you have multiple cars moving through the factory all at the same time. In computing, we call this pipelining. So, a single computer instruction has to go through these 5 stages. But with pipelining, here's the magic. All of these stages are happening at the same time, just on different instructions. So while one instruction is in the execute stage, the next one in line is already being decoded, and the one after that is being fetched from memory. This creates this constant overlapping flow, and it lets the processor finish instructions way, way more rapidly. And pipelining was really just the beginning. The next major leap was true parallelism, the ability to do multiple completely different things at the exact same time. This is the whole reason why our modern devices have multi-core processors. Instead of just having one assembly line, you now have 2 or 4 or even 16 of them, all working on different tasks simultaneously. So this brings us to right now and to the future. All the simple tricks, they've pretty much been used, and architects today are facing some of the hardest physical and logical challenges they've ever seen as they try to design the next blueprint for computing. I mean, we are seeing some absolutely incredible innovation. Instead of just adding more and more cores, architects are getting really creative. They're using powerful graphics cards, GPUs, for general computing tasks. They're designing custom chips called domain-specific architectures that do one single job, like running an AI model incredibly well. They're even starting to build chips vertically with 3D stacking to pack more power into a smaller physical space. But for every one of these new solutions, a new, tough challenge seems to pop up. That memory wall we talked about, it's actually worse than ever. The faster we run these chips, the more power they eat up and the more heat they generate, which is a real physical limit. And sometimes, the very tricks used to make chips faster can open up new problems, like the security flaws, Spectre and Meltdown, which proved that the hardware design itself could be exploited. And this is why this all matters so much. The solutions to these problems, they aren't just for academics in a lab. Efficient architecture is what will make the next wave of technology possible. Everything from smarter AI to all the countless devices in the Internet of Things to analyzing big data. It's literally the foundation for our future. So, the final question is, well, it's a big one. Our demand for more and more computing power just seems endless, but the physical limits of silicon are very real. The next generation of computer architects won't just be designing circuits. They're going to be in a constant battle to outsmart the laws of physics itself. And their success, or failure, is what will define the next chapter of technology.